Hi there. I'm glad you made it here. The room is quiet now. The world has slowed, and the air moves softly against your skin. You've done enough for today, now it's time to rest, to let thought loosen its grip. As you breathe, imagine the weight of the blanket around you, the quiet comfort of the bed holding you in place. Have you ever wondered what that weight truly is? Not just what it feels like, but what it means. Why some things fall and others resist. Why your body knows the pull of earth so intimately it feels like home. Tonight, we'll drift through that mystery together. What is mass, really? Where does it come from? Why does it matter so much that without it, the universe itself would have no shape, no stars, no us? We'll move gently, thought by thought, as if gliding through the spaces between atoms, where meaning hides in silence. And if this quiet exploration brings you peace, a small like and a soft subscribe help others find their way here too. No pressure, just when it feels right. For now, breathe easy. Let the world's weight settle kindly around you. We'll begin, slow and steady, like gravity itself. There's a certain moment that always seems to catch us off guard. When your hands curl beneath a suitcase and the weight surprises you, your muscles sigh, your breath shortens, and for an instant, you're reminded that the world resists you just a little. That quiet resistance is mass. It doesn't shout, it doesn't sparkle. It simply is a steady, invisible partner that joins you every time you lift a bag of groceries, sink into a chair, or try to nudge your sleepy cat away from your keyboard. It's the subtle way the universe reminds you that everything that exists takes up a little share of effort. And yet, for something so constant, mass is strangely hard to pin down. We use it every day without truly knowing what it means. People often speak of weight and mass as though they were twins, but they are more like cousins who look alike in dim light. Weight is the pull, the handshake between you and Earth's gravity. Mass is the you part, the amount of matter that resists being moved or hurried or slowed. One tells how much you're made of, the other how strongly the world tugs at you. If you could take your bathroom scale to the moon, your mass would stay the same. You'd still be composed of the same quiet collection of atoms, stitched together by unseen forces. But your weight, the pull of the moon's gentler gravity, would drop to a fraction of what it is here. You might grin at the smaller number, imagining yourself lighter, freer. Yet your jeans would still fit the same, and your morning coffee would still taste as heavy in your hand. The number changed, but you did not. That difference, small as it seems, shapes nearly everything we build or move. Engineers planning spacecraft must respect it. For them, mass is not a number, but a stubborn companion. Every extra gram means more fuel, more time, more patience. And even astronauts, floating gracefully in the stillness of orbit, are not free from it. Their bodies may drift in microgravity, but the mass within them still resists every nudge. To move, they must push and pull, dance slowly against air and surface like clumsy marionettes learning to waltz. You can feel it too, right here on Earth. Walking itself is a gentle dialogue with mass. Each step is a small negotiation, your foot pressing down, the ground pressing back, your weight shifting forward as your balance catches up. A toddler's wobble is a conversation unfinished, their growing body learning to speak the language of mass and motion. And as the years pass, when muscle fades and movements grow careful again, we return to that same negotiation, rediscovering how finely tuned that balance truly is. When you lift something, a backpack, a sleeping child, A small dog too spoiled to walk, you're not just raising its mass, you're working against Earth's quiet insistence. The upward pull of your arms must match the downward pull of gravity. That steady formula whispered into every corner of the world. Weight equals mass times gravitational acceleration. That's why a feather drifts and a brick drops with force. Gravity doesn't choose favorites. It only multiplies its effect according to how much there is to pull on. We don't often feel our own mass unless it argues back. You sense it in your legs when you climb a hill, in your arms when you catch a falling box, in the breath that deepens when your pace quickens. Mass reveals itself when motion changes, starting, stopping, turning, resisting. That resistance has a name: inertia. It's mass saying in its patient voice, I would rather stay as I am. The more mass something carries, the more it resists change. A truck takes longer to stop than a bicycle. A refrigerator across the kitchen floor demands more persuasion than you expected. And momentum, the energy of motion itself, is built from that same stubbornness. Mass multiplied by speed. A slow-moving bowling ball can strike harder than a fast ping-pong ball, because the universe weighs not just how quickly something moves, but how much of it is moving. Collisions, too, tell this story. Two bumper cars crash and bounce apart. Two soccer players meet midfield. Two planets pull each other across the dark, all obeying the quiet arithmetic of mass and motion. You may not think about the equations, but your body knows them in its bones. Still, when you pause to ask what mass really is, the answers begin to blur. Matter, we're told, is made of atoms, and atoms are mostly space, a delicate scaffold of particles and forces. The nucleus is dense, but even that is not solid in any familiar way. Yet, combine enough of those invisible fragments, and suddenly you have a table, a stone, a heartbeat, a world. Something that can bruise, that can fall, that can rest in your palm. The invisible becomes weight, and weight becomes comfort, the reason your feet know the ground. Without mass, there would be no stillness, no friction, no weight, no warmth. You could not sit or stand, could not catch or hold. You would drift as a cloud of particles, beautiful perhaps, but empty of shape or purpose, glitter in space, unanchored. Mass doesn't always need a scale to be known. Scientists have weighed planets by watching how their moons move, measured stars by their wobble against invisible companions, traced entire galaxies through the pull they exert on light itself. Mass may hide from the eye, but never from its consequences. It leaves fingerprints in every orbit, every balance, every motion that refuses to stop. And it behaves with a loyalty that's rare in the universe. Whether you're high on a mountain or floating above the clouds, your mass remains the same. It doesn't fade, doesn't spoil, doesn't depend on your mood. It simply is the constant note in nature's music. It might seem humble, but mass holds the world together. The push of a door, the curve of your car against the road, the firmness beneath your step, all are the quiet expressions of its presence. To understand mass is to feel the stillness within movement, the patient resistance that gives meaning to touch and form to everything we see. Centuries ago, in a small English garden brushed by evening light, a man named Isaac Newton watched an apple fall. It's a simple story, perhaps polished by time, but within it rests one of humanity's great awakenings. Newton saw in that falling apple not just fruit and gravity, but a pattern, a way to describe motion itself. He wondered why things move and why they stop. And from that wondering came laws so clear, so calm, they still echo through every corner of your day. The first speaks of inertia, the same quiet resistance we've already felt. An object at rest tends to stay at rest, and an object in motion keeps moving in a straight line unless something interferes. It's a law of laziness, really. The universe prefers what already is. Give a puck a push across smooth ice and, without air or friction, it would glide forever. Mass is the measure of that reluctance, the stubborn will of matter to continue as it was. The second law takes that stillness and adds a whisper of cause and effect. The greater the mass, the more force you need to change its motion. Force equals mass times acceleration. It's such a simple relationship that it feels like a lullaby. Push softly, move gently. Push harder, move more. A balloon and a bowling ball may both receive the same shove, but only one will cross the room with conviction. The other will barely stir. The world listens to mass before it listens to force. And then comes the third law, the one so often quoted, it sounds almost like wisdom from a fortune cookie. For every action, there is an equal and opposite reaction. But it's not about karma or consequence. It's balance. When you press against a wall, the wall presses back with the same quiet strength. Jump from a boat, and the boat drifts away. A rocket pushes exhaust downward, and the craft rises upward. Every motion is shared, no one moves alone. These three laws together form the rhythm of motion, the grammar of existence. They tell us why a pendulum swings, why planets trace their elegant paths, why the simplest touch carries both push and pull. Newton's laws stretched from the apple orchard to the moonlit sky, showing that the same invisible hands shape both. But Newton's curiosity didn't stop with motion. He wanted to understand the pull itself, the reason things fall. His law of universal gravitation said that every mass attracts every other mass. The strength of that pull grows with how much mass there is, and weakens with distance. A pebble, a planet, a star, all linked in a web of mutual attraction. This is where another side of mass emerges. Gravitational mass, the measure of how strongly something feels gravity, and how strongly it gives gravity back. Strangely, when you compare this to the mass that resists acceleration, inertial mass, they turn out to be exactly the same. It's as if the universe wrote two different job descriptions and hired the same quiet worker for both. No one knows quite why, but that perfect equality, that gentle symmetry, became the seed for Einstein's later vision of curved space-time. For Newton, it was enough to know that it worked, that the feather and the bowling ball, in a vacuum free of air, would fall together perfectly in step, bound by the same truth. It's the kind of perfection that feels less like arithmetic and more like poetry. Newton's insights opened a door that has never closed. With them, the world became predictable, not dull, but understandable. His equations guided cannonballs, shaped bridges, sent explorers to the stars. They showed that motion has a map, and that at the heart of it, mass is the key. You live inside those laws every day. You feel inertia when your car stops suddenly, and your body lurches forward, when your coffee cup tips just a little too far, when a basketball leaves your hand and arcs toward the hoop. Gravity, in Newton's view, is not only a downward pull, it's the quiet link between all things, from the apple to the moon, from your step to the spinning of the earth itself. Still, Newton's world was mechanical, made of gears and pushes, clean and solid. He treated mass as something given, an inherent property, unquestioned and dependable. It worked brilliantly so for centuries. In this clockwork universe, motion had meaning, equations had elegance, and the physical world finally seemed tame. And yet, even within that beautifully ordered cosmos, Newton revealed something remained unfinished. Small questions humming beneath the triumph. Why should gravitational mass and inertial mass always agree so perfectly, as though the universe had chosen harmony over coincidence? Why does gravity seem to reach across the vast dark instantly, tugging without a messenger, without delay? These were quiet puzzles left behind like candles still burning in an empty study, waiting for the next dreamer to notice their light. But none of this dims what Newton gave us. His work turned wonder into structure, turned falling apples and orbiting moons into a single, luminous language of motion. And at the heart of that language was mass, never boastful, never loud, simply present. The quiet strength beneath each orbit and every step, the unseen steadiness inside all that moves and all that dares to rest. And speaking of rest, you know the feeling yourself. The day has loosened its grip. You're stretched out, motionless, the room dim and still. A blanket holds the last warmth of evening. The air has settled. The phone hums once and falls silent. Somewhere nearby, a light flickers, but you do not rise to switch it off. That small, delicious heaviness keeping you still, the faint defiance of movement that is inertia, the everyday echo of Newton's idea, its mass showing its quiet nature, the body's whisper to the universe that says, "For now, I will stay." You don't need a degree to feel it. It's there in your own body, in the way your limbs hesitate before rising, in the slow roll of your head against the pillow. It's in the coffee that sloshes when your car accelerates, and in the lazy protest of a laundry basket that won't be lifted without a grunt. Inertia is the quiet law of rest, the universe's way of saying, let's not be hasty. Every object that exists holds that same reluctance. It resists change. Whether you're trying to start moving, to speed up, to slow down, or to turn, it resists. This resistance isn't mood or stubbornness. It's a property of being, something woven into the very fabric of matter. We call it inertial mass, the measure of how much an object resists acceleration. Push two things with the same force, and the one that lags behind carries more of it. More mass, more resistance. It's a universal truth you can feel through your hands. When you shove a cart through a grocery aisle or drag a box across the floor, you're in conversation with inertia. You ask the object to move, and it answers in slow motion, reluctant but polite. Picture, for a moment, a boulder and a beach ball resting side by side under the same sun. You give each a gentle nudge. The beach ball rolls off without hesitation, light-hearted, carefree, as though waiting for an excuse to dance. The boulder, though it stays, it knows its own gravity, unmoved by small talk. It takes persuasion, patience, and strength to make it shift. It holds its place like a monk, deep in meditation. Even your own body joins this dance. When you've sat too long and finally stand, your muscles protest softly, joints creak, and the first few steps feel thick with invisible glue. That's inertia again, the small tug-of-war between rest and motion. But once you're walking, it eases, momentum takes your hand, and the world becomes lighter. The hardest part is always the start. Here's a quiet marvel. Inertia doesn't care what something's made of. A bag of feathers and a bag of sand, if they weigh the same, resist motion the same way. One might float, the other flop, but when it comes to starting the journey, they are equals. Inertia is fair. It listens only to mass, not to shape or texture or story. Imagine, too, A perfect world with no friction at all. A smooth sheet of ice, and a single puck resting on its glassy surface. A small push, and it glides endlessly, unbothered by air, untouched by time. That serene glide is inertia, unmasked and pure. In our world, friction and drag interrupt the perfection, but beneath all the noise, inertia remains. It is the constant principle that gives the laws of motion their meaning. Force creates acceleration, but only if the object agrees to move. That willingness or reluctance is all in its mass. In laboratories, scientists measure this property with tender precision. They attach springs to different objects, give them equal pushes, and watch how they sway, how long they take to respond. The slower the motion, the greater the mass. You can even measure inertia without gravity, just a spring, an object, and the patient rhythm of oscillation. The longer it takes to complete a swing, the heavier the heart of that object's mass. There's beauty in that, seeing something as abstract as resistance made visible in the slow dance of a spring. It's tempting to think of inertia as personality. Some things are easygoing, eager to move. Others sit with folded arms, unmoved until coaxed with care. A heavy crate might seem proud, a small ball flighty. The more mass something carries, the deeper its roots, the stronger its silence. Watch a train begin to move. It doesn't leap forward. It hums, shudders, gathers itself, and only then begins its long, steady roll. That's inertia, stretched across steel and steam. Once it's moving, it refuses to stop, gliding for miles before coming to rest. Even the simple act of turning your car is a dialogue with inertia, your body wanting to keep going straight, while the car insists on curving. The sideways pull you feel is not the world pushing you, but your body's memory of motion, still trying to continue its story. Athletes know inertia instinctively. A sprinter exploding from stillness must overcome the body's sleepy reluctance in the first heartbeat of the race. A football soaring through air remains loyal to its path until gravity calls it home. Juggling is nothing more than a conversation between hands and inertia, keeping rhythm with objects that forever wish to keep doing what they were doing. There's comfort in this universal stubbornness. From dust to mountains, from a drifting mote in sunlight to the turning of entire planets, everything obeys the same patient law. Inertia is equality at a cosmic scale. You feel it when you roll over in bed, when you stretch, when your cup of tea sways as you stop walking. It's not just a rule, it's the way reality expresses its calm. Even our technology depends on understanding it. Inside your smartphone, tiny accelerometers sense inertia itself, little masses suspended in microscopic cages, shifting slightly when you tilt or move the device. That same principle guides spacecraft across the dark, helping them navigate through nothingness by listening to the faintest whispers of motion. Inertia, at its heart, is the universe's promise of stability. Nothing changes without cause. Objects remember their motion, their rest, their direction, until something persuades them otherwise. That quiet persistence is why you can predict where a ball will land, why bridges stand, why chairs stay still beneath you. Inertia doesn't announce itself, it hums steadily beneath all things, the same way your heartbeat hums beneath your dreams. And so, as you lie there on the couch, that lazy contentment you feel is the same principle guiding planets and satellites. Inertia is the reason you stay still when the world says, move. It's a small reminder that sometimes resisting change is part of the design. But if inertia is the whisper of rest, gravity is the pull of belonging. It's the reason your socks cling faithfully to the floor instead of drifting toward the ceiling. The reason your toast, defiant as it is, always seems to land but upside down. Gravity is the unseen tether, holding you gently against the Earth's heartbeat. It pulls oceans, moons, and galaxies into a silent waltz that never stops. Every object with mass joins this dance. You, the cat next door, the rings of Saturn, all exert a gravitational pull on one another. The strength of that attraction depends on two things: the amount of mass involved and the distance between. The more massive, the stronger the draw. The farther apart, the fainter the call. It's a simple, ancient law, first written by Newton, whose equation tells us that the pull of gravity grows with mass and fades with distance squared. It may sound mathematical, but you live inside it. When you drop a pencil, it falls because Earth's mass is calling it home. When you lie in bed, you feel the mattress press back, not because it pushes, but because the planet beneath you is holding you close. Gravity is an embrace you never stop sharing. This invisible pull also gives us one of our most elegant ways to measure mass. You can't weigh a planet on a scale, but you can watch how its moons move. Their orbits reveal the strength of the gravity that binds them, and from that, the mass of the body doing the pulling. Astronomers weigh worlds by watching their choreography. In the 18th century, a patient man named Henry Cavendish tried something astonishing. In a quiet shed, using wires, mirrors, and small lead spheres, he measured the delicate twist of a balance caused by gravity's faint touch. By studying how the spheres tugged at one another, he could calculate the force between them, and from that, deduce the mass of the entire Earth. No grand machinery, no thunderous experiment, just gravity whispering through silk and air. From those tiny deflections, the planet revealed its weight. Gravity works on every scale. It's the soft bend in your knees as you climb stairs, and the way light itself curves when it passes near distant galaxies. That bending of light, what we call gravitational lensing, is gravity's invisible fingerprint. Even when mass hides from our eyes, gravity betrays it, curving starlight around unseen hands. It's the same phenomenon that makes tides rise and fall. The moon's mass pulls at the oceans, sculpting the water into rhythmic bulges that travel around the globe. The Earth, in turn, pulls back, tugging gently on the moon, keeping it in orbit. Two partners, bound by an eternal thread. Gravity doesn't play favorites. It binds the smallest dust grain and the largest star with the same calm authority. It links the flight of a falling leaf with the spiral of galaxies. No matter how far you travel, its reach endures. Through its pull, we can even weigh what cannot be seen. When astronomers measure how stars orbit the centers of galaxies, they expect the outer ones to move more slowly, but they don't. They spin just as swiftly, as though held by invisible hands. That hidden grip belongs to something we cannot see: dark matter. We know it exists not because it glows, but because gravity refuses to lie. Gravity tells the truth even about monsters. Black holes, those dense wells of collapsed stars, reveal their presence not through sight, but through gravity's choreography. Nearby stars curve and swirl around emptiness, their motion declaring what light cannot show. Gravity is often described as a downward force, but that's only our local version of its story. In truth, gravity is the sculptor of everything, with form the reason planets are round, why galaxies cluster, why stars find one another in the dark. It is the architect of structure, building the universe grain by grain, orbit by orbit. Without it, there would be no mountains, no oceans, no steady orbits to cradle life. The universe would unravel into a lonely cloud of particles. drifting apart forever. With gravity, there is connection. With mass, there is conversation. Even now, as you sit here, you are part of that quiet dialogue. The earth pulls you, and you pull it back, equally and opposite, two participants in the same ancient exchange. Every object, every motion, every heartbeat is tied by gravity's unseen thread. The sun's gravity keeps the earth in its gentle loop. Jupiter's vast pull tugs subtly on the path of every planet. Stars pull at one another. Galaxies sway together. Nothing floats entirely free. Every movement is part of a greater choreography, a harmony of mass and motion stretching across time itself. Mass is the listener, gravity the voice. Together they keep the cosmos in rhythm, an endless duet of pull and reply. You can hear it in the long sigh of the tides, in the gentle sway of a hammock on a still afternoon, in the slow surrender of a leaf falling through warm air. Every motion, every pause, is part of that conversation. Gravity speaking softly through mass, mass listening and answering in the only language it knows, weight and movement, silence and return. It's a lullaby older than stars, a song of attraction and balance that never truly ends. Now, take a breath and imagine yourself inside that same rhythm. You're perfectly still, wrapped in the quiet comfort of your own small corner of the universe. A blanket rests against your skin, the air holds steady, and for a moment it feels as though even time has stopped to listen. But within you, beneath the calm surface, nothing is still. Every cell hums with motion. Atoms spin, collide, and shimmer. Particles flash in and out of being like sparks beneath the waves. You are made of storms so small they feel like peace, of constant movement folded into stillness. And that motion, that endless hidden dance of energy, is what gives you mass. Einstein discovered that your mass is your energy, not metaphorically, but literally. His small, elegant equation, E equals mc squared, revealed that mass and energy are two sides of the same shimmering coin. Energy can become mass, and mass can unfold back into energy. The C in that formula is the speed of light, an almost unthinkable number, about 300 million meters every second. Square it, and the number becomes enormous, so large that even the smallest bit of matter holds a reservoir of energy vast enough to light a city. But this energy rarely escapes. It prefers to stay quietly folded within the structure of matter, content to hum instead of roar. Only in extraordinary circumstances, nuclear reactions in stars, or the experiments of humans who have learned to imitate them, does a trace of that mass unravel into radiant power. Every time the sun shines, hydrogen atoms fuse into helium, and a little piece of their mass disappears, turning into light and warmth that cross space to touch your face. It's a small trade, just a fraction of mass, exchanged for brilliance. But across the sun's vast body, it becomes enough to sustain life itself. Einstein's insight runs both ways. If mass can become energy, energy too must have mass. When something gains energy, when it warms, spins, or gathers speed, it becomes ever so slightly heavier. Not enough for you to feel, of course. A hot cup of tea weighs infinitesimally more than an iced one, but the physics is real and quietly faithful. Energy, in all its forms, heat, motion, light, adds a whisper of weight to the world. In particle accelerators, where fragments of matter race near light speed, that whisper becomes a song. Particles collide, and energy condenses into new matter, fleeting but real. A flash of motion becomes a family of new particles, each with mass, charge, and personality. It looks like creation, but it's really transformation, the universe rearranging its energy into shape. In that sense, mass is what happens when energy decides to rest, when it stops racing and agrees to stay in one place, to have form, to be touched. Mass is energy caught in a moment of stillness, a promise to linger a while. This realization stretches far beyond the laboratory. It means that everything you see, everything you are, is energy in a slower, gentler costume. You are light that has chosen to take its time. Matter is simply energy that's settled down, agreeing to move through the world more quietly. Einstein reached this idea not through experiment, but through thought, by watching the world in his mind and noticing how motion and light converse. He saw that as an object gathers energy, it becomes harder to move, harder to stop. Its inertia increases. That resistance is mass. Energy, when bound and reluctant, behaves like matter itself. And because energy and mass are equal, gravity listens to both. The curve of space that holds the planets in their paths bends not just for heavy objects, but for light itself. A beam of sunlight passing near a star bends in its course, because even massless light carries energy, and energy makes space bow in respect. It's a strange thought that light, which seems so free, is gently steered by gravity's invisible hand. But it's true, and it was this truth that led Einstein to his deeper vision of the universe, general relativity, where gravity is not a pull, but a curvature, a bending of space-time itself by energy and mass. You might wonder why, if matter is packed with such tremendous energy, the world doesn't burst apart in radiance. Why the chair beneath you doesn't dissolve into light. The reason is simple and merciful. The conversion from mass to energy requires perfect conditions, temperatures, and pressures found in stars, or in the dance between matter and its mirror opposite, antimatter. Only in those extremes does matter surrender fully to its luminous self. When a particle meets its antiparticle, they vanish in a breath of photons. No fragments, no remains, just pure energy released into the world. It's the universe's cleanest equation at work. Every gram of mass becomes light, even in the atoms that make you. This quiet exchange continues. The total mass of an atom is not simply the sum of its parts. When protons and neutrons bind together in the nucleus, a little bit of mass disappears, replaced by the energy that holds the atom together. That missing weight, the mass defect, is the signature of unity, the price paid for cohesion. Black holes obey this rule as well, though on a grander, darker scale. As matter falls inward, some of its mass transforms into radiation, sometimes shooting outward in thin, furious jets, before disappearing forever. The remainder deepens the black hole's gravity, folding energy into the weight of darkness. Even there, Einstein's equation whispers, nothing is lost, only changed. There's comfort in that thought. Energy and mass are not enemies or opposites, but reflections of the same thing, the pulse of reality, seen from different angles. Energy can glow, surge, or race. Mass can rest, hold, and endure. But beneath both lies one truth. They are the same song in different tempos. If you could listen closely enough, you'd hear it everywhere. The hum of light in a morning window, the warmth of your body as you breathe, the faint pressure of the earth beneath you. All of it is energy choosing form, moment by moment. Even time joins the dance. A clock that moves faster or deeper in a gravitational field ticks differently because energy and mass alter the shape of space-time itself. The more energy a thing holds, the more it bends the weave of the cosmos around it, slowing the rhythm of time. Einstein's small equation, so spare it could fit on a napkin, contains the secret pulse of the cosmos. It tells us that nothing is ever truly still, that even in silence, matter hums with stored possibility. Every pebble, every breath, every faint shimmer of sunlight carries a hidden storm of energy folded within it. When you lift a stone, when you stir your tea, when you look toward the sun through a gauze of cloud, you are touching energy at rest, motion paused into form, patience made visible. What we call mass is simply energy waiting, the universe holding its breath in your hand. And if you were to look closer, much closer, you'd find that this calm solidity is an illusion of scale. An atom, that smallest whisper of being, seems far too small to matter. Millions could line up across the width of a single hair and still have room to dance. Yet within that tiny architecture lies the foundation of everything, the bones of mountains, the depth of oceans, the warmth in your skin. Each atom, light as it is, carries genuine weight, not the kind you can feel pressing on your palm, but the kind that holds the world together, that gives your body its gentle gravity against the chair where you rest. When we speak of atomic mass, it's tempting to imagine a simple sum, the weight of its parts, neatly added up, like coins in a pocket, protons, neutrons, electrons. But nature rarely accepts tidy arithmetic. Atomic mass is not just the sum of its pieces. It's also the story of their relationships, their tension, their closeness, the energy that binds and hums within them. Every atom has three main characters. The protons and neutrons dwell together in the heart, the nucleus, while electrons flit around them in a soft blur. Like sparks in a tiny storm, the electrons make chemistry, light, electricity. They create color and connection, but they are featherweight things. Each one is about 2,000 times lighter than a proton. If an atom were a sandwich, the electrons would be the sesame seeds scattered on top, important, decorative, but barely adding weight. Almost all of an atom's mass comes from its nucleus, that dense and secretive center where the protons and neutrons live. These two particles, called nucleons, hold nearly all the atom's heft. They are not heavy because they are large. On the contrary, they are unimaginably small, but because of the energy folded inside them. Einstein taught us that mass is energy, and the nucleus hums with it. But here lies one of the strangest truths in all of nature. If you could take each proton and neutron out of the nucleus, weigh them separately, and then add their masses together, you would get a number slightly larger than the actual mass of the nucleus. Something is missing. That missing piece is called the mass defect. The mass hasn't vanished, it has transformed. It has become the energy that glues the nucleus together. The difference between what was and what is has turned into what we call binding energy, the invisible cement of existence. This energy is what keeps the protons each positively charged, each eager to repel its neighbors from flying apart. The only reason they don't burst away from each other in electromagnetic rebellion is the strong nuclear force, one of the four fundamental forces of the universe. It lives at impossibly small scales, operating only within the confines of the nucleus, yet it is fierce enough to hold creation together. Imagine it as an unseen bouncer in the atomic club, holding the peace while the protons grumble and push. The strong force overwhelms their repulsion, binding them with an embrace so tight that part of their mass melts into the energy of the bond itself. That lost mass is not gone, it's simply keeping the family together. This delicate trade between mass and energy is why nuclear reactions are so powerful. When a large nucleus splits apart, or when smaller ones fuse together, the difference in binding energy is released into the world as light or heat. It's what makes the sun shine, what powers the stars, what hums quietly in reactors here on Earth. The tiniest rearrangement of the nucleus releases oceans of energy. Not all elements are equal in this dance. Iron, for instance, sits near the summit of stability. Its binding energy per particle is so balanced, so perfect, that it neither wants to fuse with others nor split apart. It's the cosmic dead end of nuclear alchemy. Stars live and die chasing this balance, burning lighter elements to reach iron, and once they do, their furnaces sputter out. Iron is the sigh at the end of a stellar life, a quiet exhale that says, no more fuel to give. Across the periodic table, the pattern continues. Heavier atoms have more protons and neutrons, yet their total mass is never just arithmetic. Uranium, with its 92 protons and a cluster of neutrons beside them, carries immense mass, but not simply the sum of its ingredients. The more tightly those particles are bound, the more energy and therefore mass has been quietly exchanged. Atomic mass, then, is not just a count. It's a conversation between matter and motion, between structure and release. Even atoms of the same element can differ slightly in this story. These are isotopes, siblings with the same number of protons, but different numbers of neutrons. Carbon, for instance, comes mostly as carbon-1,2, but a small fraction of carbon-1,3 and carbon-1,4 exist as well. Those heavier versions change how the atom behaves, how long it lasts, and how it whispers secrets of time to us. We use that whisper, carbon-1,4 decay, to date ancient wood, bones, and memories. Every number on the periodic table is not a single weight, but an average of all these forms. Chlorine, for instance, appears as 35.5 because nature blends its isotopes, mixing the lighter and heavier versions in precise, graceful proportion. If you peer deeper still inside the protons and neutrons themselves, you find that even they are not truly solid. They are made of smaller things, quarks, and the energy that binds them, carried by particles called gluons. And here's the astonishing part. Most of a proton's mass doesn't come from the quarks at all, but from the swirling energy of the gluons between them. It's as if three dancers are so light they barely touch the floor, yet the motion of their dance shakes the entire room. At every level, mass is not so much stuff as it is motion contained. It's the rhythm of energy, caught in a loop, the potential that hums between connections. When atoms link together into molecules, even then, small changes in mass occur. Bonds form, energy is released, and the new structure weighs a whisper less than its parts did before. Chemistry, too, follows the same old rule. Nothing ever adds up exactly, because energy and mass are always trading places. So when you think of atomic mass, don't picture weight on a scale. Picture balance, the eternal negotiation between what's bound and what's free, what's energy and what's matter. Atomic mass is the quiet handwriting of that compromise, recorded in every grain of dust, every cell, every star. To grasp how mass behaves in motion, imagine you're sitting on a train that glides through the countryside, smooth as thought. You lift a cup, feel its weight steady in your hand. Outside the window, another train rushes by, and for a heartbeat, you can see someone doing the same, sipping tea. gazing outward. From your seat, they seem to be racing past. From theirs, you are the one who moves. And somehow, both of you are right. This is the world Einstein invited us, into a world where motion is relative, where time can stretch and space can bend, where mass seems to change depending on how you look at it. For a long time, people thought that as objects approached the speed of light, their mass increased, as though they were gaining weight from sheer effort. It's a vivid image, a spaceship growing heavier the faster it flies. But that's not quite the truth. The mass itself, the intrinsic resting mass, doesn't change. What grows is the energy. There are two ways to talk about mass. The first is rest mass, the steady, unchanging identity an object carries when still. The second, older idea, is relativistic mass, which folds the growing energy of motion into the concept of weight. Physicists today prefer the simpler view. Mass stays constant, but as an object speeds up, its total energy rises. The more energy it gathers, the harder it becomes to push faster. At everyday speeds, this difference is invisible, but near the speed of light, it becomes dramatic. You can pour endless energy into a particle, and instead of simply going faster, it becomes more resistant to change. It doesn't grow heavier, it becomes steadier, harder to budge, as if time itself is cushioning its motion. Einstein's special relativity revealed that space and time are not separate threads, but a single, woven fabric, space-time. When you move quickly through space, you move more slowly through time. From your perspective, everything feels normal. But to someone watching from a distance, your time has slowed. Your space has compressed. Imagine again that beam of light bouncing inside the moving train. To someone aboard, it moves straight up and down. To someone watching from outside, the light traces a diagonal path, longer than it appeared inside, because the speed of light is constant for everyone. The only way the math and the universe can agree is if time on the moving train slows down. And it does. This isn't a theoretical curiosity. It's woven into daily life. The satellites orbiting high above the Earth must account for this bending of time. Without the corrections of relativity, your phone's GPS would drift off by kilometers every day. Einstein's equations keep your directions straight as surely as they keep galaxies curved. At the highest energies, in places like the Large Hadron Collider, protons whirl close to the speed of light. Their rest mass stays the same, but their energy becomes immense, altering how they collide, merge, and break apart. Cosmic rays from deep space carry this energy too, racing through the atmosphere, ticking more slowly by their own clocks, yet obeying the same laws that hold your teacup steady. Relativity ties all of this together. What you see as motion is energy revealing itself. What you feel as resistance is energy's loyalty to mass. The faster you go, the more you sense how deeply energy and matter are intertwined, not changing each other, but expressing the same truth from different sides. Even light, which has no rest mass at all, carries energy and momentum. It can push, pull, bend under gravity, and sculpt the shapes of galaxies. Mass may be the body, but energy is the soul, and together they write the rules of the cosmos. Rest mass, then, is a kind of stillness, a quiet declaration written into the heart of every particle that says, "This is who I am when nothing moves." Energy can stir it, heat it, set it dancing with light, but beneath all that motion, the core identity endures. Mass is energy at rest. Energy is mass awakened. the same melody played at different tempos. So when you picture a ship racing through the deep dark at nearly the speed of light, don't imagine it swelling beneath the weight of invisible burdens. Imagine it blazing softly with energy, wrapped in stretched time, carving its path through space-time's supple fabric. Its mass hasn't changed, it's simply singing the universe's rhythm in full volume, moving like a single pure note, sustained in a song too immense to ever finish hearing. And somewhere beyond that glowing trajectory lies another, quieter form of magic, one that hums not in motion but in stillness. It doesn't sparkle or flash, it hides, silent and constant, stretching through every inch of the cosmos. You can't see it, can't touch it, but it is everywhere, woven through every atom, every breath, every star. It's not gravity, though gravity's pull is its distant cousin. It's something subtler, stranger, and more mysterious still. The Higgs field, the invisible presence that gives the universe its weight and matter its meaning. To understand it, you have to let go of the idea that space is empty. In truth, there is no such thing as emptiness. Even the quietest vacuum hums with activity, a restless ocean of invisible fields rippling with potential. Each force, we know, the electromagnetic, the gravitational, the strong and weak nuclear, comes from its own field, stretching across space. Light itself is the dance of the electromagnetic field. Gravity is the curve written into the geometry of space-time. And then there's the Higgs field, subtle and peculiar, giving shape to one of the most fundamental properties of all, mass. The Higgs field is not a ghost or a mist drifting through the air. Think of it instead as a cosmic kind of molasses, filling the universe from end to end. Now imagine a particle, say, an electron trying to move through it. Some particles glide through easily, like marbles across polished glass, barely slowed at all. Others wade through as though wearing boots full of honey, pulled and slowed by the stickiness of the field. The more strongly a particle interacts with this cosmic molasses, the more resistance it feels, and the heavier it becomes. There's another way to picture it. One physicist's love for its charm. Imagine a crowded party. The room is filled with people chatting quietly, standing shoulder to shoulder. Now a celebrity walks in. The crowd stirs. People gather. Everyone wants a moment, an autograph, a picture. The celebrity tries to cross the room, but moves slowly, constantly stopped by attention. Meanwhile, a quiet stranger slips through unnoticed, crossing easily to the other side. In this story, the room is the Higgs field, the crowd is the particles' interaction with it, and the resistance, how much they're slowed, is their mass. Mass, then, is not a built-in feature. It's not something a particle carries in its pocket. It's the result of relationship of how the particle moves through this invisible ocean that fills the cosmos. The more it interacts with the field, the more it seems to weigh. This idea began taking shape in the 1960 seconds, when physicists like Peter Higgs, Robert Brout, and Francois Englert were facing a stubborn problem. The equations describing fundamental forces worked beautifully until they tried to include mass. With mass added, the mathematics broke apart. It was as if nature's balance sheet refused to balance. To fix it, they proposed a radical idea. What if mass wasn't inherent at all? What if it emerged from a field that pervades all of space? That field, once introduced, made the equations whole again. Particles could now have mass through their interaction with it, without breaking the elegant symmetry of physics. The idea became the cornerstone of what we now call the Standard Model, the great framework describing nearly everything in the subatomic world. Without the Higgs field, many particles would move at the speed of light, never slowing, never binding into atoms or molecules. There would be no chemistry, no matter, no life. The universe would be pure radiation, bright, brief, and utterly uninhabitable. For decades, the Higgs field remained theory, a perfect solution, but an invisible one. A field, after all, can't be caught or seen directly. But if a field exists, it must have a particle that represents its vibration, its brief sparkle in reality. The electromagnetic field has photons. The Higgs field should have Higgs bosons. Finding that particle became one of the greatest scientific adventures of the modern age. To glimpse it, scientists needed to recreate the conditions of the early universe moments after the Big Bang, when energy and matter blurred together. That meant smashing protons at unimaginable speeds. Deep beneath the border of France and Switzerland, the Large Hadron Collider, a vast underground ring more than 25 kilometers around, was built for exactly this purpose. Inside, streams of protons whirl in opposite directions, guided by powerful magnets, until they collide head-on at nearly the speed of light. Each collision is a miniature cosmos, a flash of energy dense enough to summon new particles into being. On July 4th, 2012, after years of waiting, watching, and refining, scientists at CERN announced that they had found what they had been searching for, a new particle with a mass of about 125 giga-electron-volts, just where the Higgs boson was predicted to be. Around the world, physicists smiled, cried, and raised glasses of champagne. In the audience, Peter Higgs himself wiped tears from his face. The field that bore his name had finally revealed itself not just as mathematics, but as reality. The discovery was more than confirmation. It was revelation. The Higgs field wasn't just a clever fix for broken equations. It was part of the universe's architecture, the quiet mechanism that gives substance to everything. Without it, nothing would have weight. Nothing would hold shape. We had, in a very real sense, found the reason that anything is. The Higgs boson, though, is a fleeting creature. It vanishes almost as soon as it appears, decaying into lighter particles, photons, quarks, and others that can be detected only as traces, like footprints left in fresh snow. Physicists never see the Higgs boson itself, only the echoes of its passage, and from those patterns, they reconstruct its brief existence. Yet those whispers were enough. The footprints matched the theory almost perfectly. Still, the Higgs field doesn't account for all the mass we see. Most of the mass in the protons and neutrons inside your body doesn't come from the Higgs field at all. It comes from the furious energy of the strong nuclear force, the dance of quarks and gluons inside those particles. The Higgs field gives mass to the quarks themselves, to electrons, and to the heavy W and Z bosons. But the rest, the bulk of your weight, the heft of every mountain and planet, comes from energy bound tightly within matter's heart. In the modern picture of physics, every particle is not a tiny marble, but a vibration, a ripple in some deeper field. The electron is a small wave in the electron field. The photon is a ripple in the electromagnetic field. The Higgs boson is a pulse in the Higgs field. The universe is a sea of invisible energy, overlapping, interacting, breathing. The so-called vacuum of space is not empty at all. It shimmers with unseen activity, alive with potential. And yet, the discovery of the Higgs boson wasn't the end of the story. It was a beginning. Because now we must ask, why does the Higgs field have the strength it does? Why not stronger, weaker, or absent altogether? Could there be other, similar fields, siblings of the Higgs waiting in the dark? The answers could point us toward new physics, toward the next layer of understanding beneath the Standard Model's neat, shimmering surface. Still, for a moment, it's worth pausing simply to marvel. Space itself, something we once thought of as emptiness, turns out to be the very thing that gives matter its substance. Every second, in every corner of the universe, particles wade through the Higgs field and, in doing so, become real. They gain inertia, weight, identity. The universe gives them form. It's as if existence itself is a dance floor filled with unseen resistance. Some dancers glide freely, others stumble as if caught by invisible threads. Mass is not an accessory, it's the choreography written into how each dancer meets the floor. Consider the photons, the eternal travelers. They have no mass at all, and so they move unhindered at the cosmic speed limit, 300 million meters per second. Because they do not couple with the Higgs field, they are forever free, moving through space without ever slowing. If light had even the faintest trace of mass, it would be a different world. Beams would fade faster, colors would shift, stars would dim, but light is perfect in its freedom, massless and swift, carrying news from galaxies that died before our species began. The W and Z bosons, by contrast, are the heavyweights of the subatomic ballroom. They carry the weak nuclear force, the quiet mechanism behind radioactive decay. These particles are short-lived, massive, and slow by quantum standards. The W boson weighs around 80 giga-electron volts, and the Z boson around 91, nearly 100 times heavier than a proton. Imagine trying to run a race in a suit of armor. They flicker briefly into being and vanish again. Why are they so heavy while photons are not? Because they interact deeply with the Higgs field. The photon passes through untouched, but the W and Z bosons couple strongly with it. The more they interact, the heavier they become. Their mass limits how far the forces they carry can reach. The weak force acts only across subatomic distances so small you could stack 1 billion of them inside a single atom. It's their mass that makes the weak force weak, just as the photon's lack of mass makes electromagnetism reach from star to star. This delicate balance, some particles heavy, others weightless, is part of what makes the Standard Model so elegant. Mass defines range, defines influence, defines behavior. It is not simply a number, it is a role in a story. And then there are the neutrinos, the wallflowers of the particle world. Shy, nearly invisible, slipping through everything without a trace. Trillions of them pass through your body every second, through your chair, through the Earth itself. They come from the sun, from dying stars, from the quiet decay of atoms deep underground. You will never feel them. You will never stop them. For decades, physicists believed neutrinos were completely massless, tiny ghosts with no substance at all. But then came a surprise. Neutrinos were observed to change identity as they traveled, switching between types, a process called neutrino oscillation. For this to happen, they must have mass, however small. The discovery shook the foundations of physics. Their mass is tiny, so small we still haven't measured it precisely, but its existence proves the Standard Model incomplete. Something else, something subtle, is at play. Neutrinos may gain mass from the Higgs field, or from another hidden mechanism, a whisper from physics beyond our current reach. Some scientists even suspect neutrinos hold clues to why there is more matter than antimatter in the universe, why something, instead of nothing, exists. They may even connect to the riddle of dark matter, the unseen mass that outweighs all visible stars combined. Neutrinos, could be messengers, carrying secrets from the first moments after creation. And so, the story of mass becomes one of relationships. Some particles carry it boldly, shaping the world with their weight. Others remain light, free to travel the cosmos unbound. The photon never rests. The W and Z flicker and vanish, and the neutrino, half ghost, half whisper, slips quietly through the spaces between. At the center of it all is mass, not just as heaviness, but as connection. It decides how a particle moves, how it interacts, how long it lives. It's not merely a property, it's a language of behavior, a grammar of the universe. In this great cosmic dance, those who wish to travel far must remain weightless. Those who wish to act powerfully must bear the burden of mass. And some, those delicate neutrinos, walk the line between both, telling a story still unfinished. Mass is not simply what things have. It is what they are in motion through space, what they become in conversation with the invisible fields that fill the void. The Higgs field does not just give weight to the world, it gives it character, texture, and grace. Even now, as you sit in the quiet, that field surrounds you. Every atom in your body hums within it. Every particle you are is slowed, shaped, given identity by its gentle touch. The same field that brushes the edge of galaxies also moves through you, making you real, making you part of the same invisible dance that began with the birth of the universe. Mass and matter, two words that often travel together, hand in hand, through sentences, textbooks, and late-night conversations. They sound like siblings, close, familiar, almost interchangeable, but they are not the same. One is the stuff of the universe, the tangible fabric that fills space. The other is a property, an invisible signature that tells us how that stuff behaves. Once you see the difference, the world begins to make a softer kind of sense. Matter is what you can touch, lift, sip, or stumble over in the dark. It's everything made of atoms, stones, oceans, clouds, your heartbeat. It's the furniture of existence, the substance that occupies space and refuses to share it. Mass, however, is not stuff at all. You can't scoop up a cup of mass or pour it into a beaker. Mass is a trait, a measure of how resistant something is to being moved, how strongly it feels gravity, how firmly it sits in space-time. It's the flavor of matter, the melody to its structure. You can have one without the other. Some things that are not matter still have mass-like effects. Others are matter, yet nearly weightless. Take light photons, the small quanta that illuminate everything. They are not matter. They have no rest, mass, no stillness. You could chase one across the universe and never catch it, because it cannot stop. Yet these weightless travelers carry momentum, push on sails, warm your skin, and feed the green machinery of life. Photons can knock electrons loose from metal, steer spacecraft through the pressure of sunlight, and reveal the shape of distant stars. They act without possessing mass in the usual sense. Their energy gives them influence, even as their lack of rest mass lets them move at the ultimate cosmic speed, light speed, the universe's unbreakable limit. If photons had even a whisper of mass, the world would change. Light would tire as it traveled, colors would fade with distance, and the oldest starlight might never reach us. But photons remain perfectly massless, born already at light speed, forever racing through time's open hand. Matter, by contrast, is made from particles that can rest. Electrons, quarks, protons, neutrons. Their combinations form the atoms and molecules that make up everything we see. These particles have rest mass, which means they can simply be sitting still, waiting, taking up space. That stillness defines them. Their mass shapes how they fall, collide, bind, and balance. It's what makes your teacup settle on the table and not float away with the morning breeze. But mass isn't the same as amount. A fluffy cloud can contain more matter than a stone, and yet weigh far less. A handful of uranium holds more mass than a bucket of feathers. What matters is not volume but density, how tightly the energy and matter are packed together, how strongly they resist motion or bend gravity's weave around them. Then there's energy, the restless partner to both. Einstein showed us they are entwined, that mass and energy are simply two faces of the same coin. E equals mc squared. That small equation holds everything. Mass can become energy, and energy can behave as mass. Even a beam of light bouncing between mirrors inside a sealed box adds to the box's weight ever so slightly. The trapped photons lend their energy to the system's mass. The same is true within you. The mass of your body doesn't come mostly from the particles themselves, but from the energy inside them. A proton, for instance, weighs far more than the total of its 3 tiny quarks. Most of its mass comes from the ceaseless motion and binding energy of the strong nuclear force that holds those quarks together. You are built from that energy, motion frozen into form, tension held in harmony. So mass isn't substance. It's the quiet shadow cast by energy and interaction. It tells us how strongly something clings to its place in space-time, how reluctant it is to move, how deeply it tugs on gravity's fabric. You can't ladle it or pour it. You can only feel it through resistance, through pull, through the measured persistence of weight. This distinction becomes essential when we turn to the unseen. Dark matter, for example, is named not because it glows black, but because it refuses to shine at all. We call it matter because it seems to have gravitational pull, because galaxies spin too fast. Stars stay bound when they should drift away. Something invisible must be adding weight to the universe. But whether this something is made of unknown particles or of some exotic form of energy masquerading as mass, we still don't know. Even light, though massless, can exert pressure. When photons strike a surface, they transfer momentum not because they weigh anything, but because energy always carries influence. It's one of the small wonders of physics. Massless particles can still push. The universe never wastes a rule. It simply finds new ways to play by it. In everyday speech, we mix these terms freely. You say something has a lot of mass when you mean it's heavy or it's big. And for daily life, that's perfectly fine. But physics is patient and precise. Matter is the stuff. Mass is the measure of how that stuff behaves in the presence of forces. And energy, the great trickster, is what binds, moves, and sometimes hides as either of the other two. Think of matter as the furniture of the universe. Mass is how hard it is to push that furniture around. Energy is the unseen hand that keeps rearranging it when no one's watching. That difference also helps us understand why some forces act on certain things but not others. The Higgs field, for instance, couples only with particles that have mass. That's why light glides through it untouched, while electrons and quarks feel its drag. Gravity, meanwhile, is far less selective. It acts on everything: mass, energy, even light itself bending paths, curving space, shaping galaxies. Once you understand the distinction between mass and matter, the universe becomes clearer, more intricate, more alive. The stars, the air, the water, all are made of matter. Their behavior, their inertia, their gravity, that's mass at work. It's how the universe keeps its rhythm, how it resists chaos, how it holds shape. Even your morning cup of coffee holds this secret. The liquid, the ceramic, the rising steam, these are matter, but its mass is something subtler. It's the pattern of particles and energy, each one resisting motion just enough to make your cup feel real in your hand. Mass isn't what your coffee is. It's how your coffee behaves in the great choreography of forces that governs everything. Now imagine trying to weigh something you cannot touch, a whale deep in the ocean, perhaps too vast to lift, too hidden to see. You'd watch the waves it makes, the ripples left in its wake, and from those infer its weight. That's how we weigh the universe. Galaxies, clusters, superclusters. None of them will ever sit on a cosmic scale. But gravity leaves clues. Every object with mass pulls on every other. Those pulls shape orbits, curves, and light itself. By studying the motions of stars, the clustering of galaxies, and the bending of distant starlight, we can deduce the invisible mass that holds everything together. When astronomers first mapped the motion of stars in galaxies, they expected a pattern like our solar system: inner stars moving fast, outer stars slower. Instead, they found something astonishing. The stars far from the galactic core were moving just as quickly as those near the center. The visible matter wasn't enough to explain it. Something unseen was tugging on them. Something with mass, but no light. Thus was born one of the greatest mysteries in modern physics: the problem of the missing mass. In galaxy after galaxy, the visible stars, gas, and dust accounted for only a fraction of the total gravity observed. The rest, nearly all of it, was invisible. This unseen material became known as dark matter. Dark matter neither emits nor reflects light. It doesn't glow, it doesn't scatter, it doesn't whisper in electromagnetic waves. Yet we can trace its presence through its influence, how it sculpts galaxies, how it binds clusters, how it weaves the cosmic web itself. By studying how galaxies move within clusters, scientists can estimate how much mass is required to keep them bound together. Every time they do, the numbers tell the same story. Most of the mass is missing from view. The stars are only the frosting on an invisible cake. Gravity also lets us see this darkness through another phenomenon: gravitational lensing. When light from a distant galaxy passes near a massive object, the gravity of that object bends the path of the light, just as glass bends the path of a beam through a lens. Sometimes the effect is dramatic, complete rings of light called Einstein rings. Sometimes it's subtle, a gentle distortion that can only be measured statistically. But every bend reveals mass, visible or not. Gravitational lensing doesn't care what kind of matter causes it. Normal matter, dark matter, it all curves space-time the same way. By measuring how light bends, we can map where the mass truly lies. These cosmic maps show something profound. Most of the universe's mass is invisible, forming vast halos around galaxies, linking them in filaments and clusters that stretch across billions of light years. One of the most striking pieces of evidence came from a collision known as the Bullet Cluster. Two galaxy clusters collided. Their hot gas ordinary matter slowed and heated, while the invisible dark matter passed through, untouched. Observations of gravitational lensing showed the mass following the dark component, not the glowing gas. The result was clear. The unseen outweighs the seen. In a typical galaxy, only about 15% of its total mass shines as stars or glows as gas. The remaining 85% hides in shadow. The universe, for all its glitter, is mostly darkness. And yet, even with all this unseen weight, space remains astonishingly empty. Galaxies are mostly void, with more nothing than something between their stars. If the sun were shrunk to the size of a tennis ball, the nearest star would be another tennis ball over 700 kilometers away. The universe carries immense mass, but it is a whisper stretched thin across an endless reach. What we call empty space is, in truth, filled with energy, fields, and gravity's endless reach. Matter gives shape to the world. Mass gives that shape resistance. And gravity turns both into the rhythm by which the cosmos moves. So when you look at the stars, remember, most of what holds them there is invisible. Matter builds the stage. Mass writes the choreography. Together they make the universe dance, weightless and heavy all at once. How do we weigh the universe? Not with scales or hands, but with patience, with light, with motion, with the slow language of gravity. We listen to how space bends, how galaxies drift, how light curves on its way to us. We measure not what we can touch, but what we can infer. Because the universe, as it turns out, keeps most of its secrets hidden. Mass is not just what we see, it's what holds everything together. The stars that dazzle us, the planets, the clouds of glowing gas, they make up only a small fraction of the cosmic story. The rest, the overwhelming majority, is invisible, and yet it shapes everything. It is there in the way galaxies spin, in the way starlight bends, in the silent cohesion of the cosmos. This unseen presence has a name: dark matter. It doesn't glow or reflect. It doesn't whisper through radio waves or scatter light. It doesn't respond to any of our telescopes, no matter how sensitive or clever they become. But its gravity speaks volumes. Dark matter is the quiet backbone of the universe, the unseen weight that gives form to galaxies and structure to everything that exists. At first, the idea sounded like a trick, a cosmic sleight of hand. How could something invisible make up most of the universe? But dark matter wasn't imagined out of wishful thinking, it was demanded by the numbers. When astronomers measured the way stars moved inside galaxies, the math didn't fit. The visible matter, the stars, gas, and dust, wasn't nearly enough to hold those galaxies together. Something else was doing the pulling. Spiral galaxies were the first clue. Picture them, enormous pinwheels of stars, graceful and glowing. You'd expect the inner stars, close to the center, to orbit quickly, and the outer ones to drift more slowly, just as Mercury circles the Sun faster than Neptune. But when astronomers plotted the speeds of stars at different distances, the pattern defied expectation. The outer stars weren't slowing down at all. They were moving almost as fast as the inner ones, too fast to be held by visible gravity alone. According to Newton's laws, those stars should have flown off into the dark, yet they didn't. Something unseen was anchoring them, wrapping each galaxy in a halo of invisible mass. These halos, immense and spherical, contained several times more mass than all the stars and gas combined. Every galaxy, it seemed, was floating in a hidden ocean of gravity. The idea gained strength from galaxy clusters, the grand congregations of hundreds or thousands of galaxies bound together. In the 1000 930 seconds. An astronomer named Fritz Zwicky studied one such cluster, the Coma cluster. He found that the galaxies inside were moving far too quickly to stay together, given the amount of visible matter. By all rights, the cluster should have flown apart. Zwicky proposed that some dark matter must be providing the extra gravity to keep everything intact. His peers mostly ignored him. The instruments of the time couldn't confirm his bold claim. But as the decades passed, observation after observation began to prove him right. Then came one of the universe's most beautiful tricks: gravitational lensing. When light from a distant galaxy passes near a massive object, the gravity of that object bends the path of the light, distorting its image. It's like looking through warped glass, a cosmic mirage. By studying those distortions, astronomers can measure how much mass is causing them. Time and again, the bending of light revealed more mass than the visible stars and gas could account for. The universe, it seemed, was far heavier than it appeared. One of the clearest demonstrations came from an extraordinary event called the Bullet Cluster, a collision between two galaxy clusters. When they crashed, the clouds of hot gas, visible in X-rays, slowed down and piled up, like two cars crumpling on impact. But when scientists mapped the mass using gravitational lensing, they found that most of it had passed straight through. The invisible component hadn't collided at all. It had drifted ghost-like, unaffected, proving that the majority of the mass wasn't in the visible matter, but in something else entirely. So what is dark matter made of? That's the great unanswered question. We know it exerts gravity. We know it shapes galaxies, but we don't know what it's made from. The leading theories suggest it could be made of particles, new kinds of particles that don't interact with light or ordinary matter except through gravity. They would be heavy, stable, and quiet. One popular idea imagines WIMPs weakly interacting massive particles. They would have mass, but only the faintest ability to interact with normal matter, making them almost impossible to detect. Others propose axions, unimaginably light particles that could fill the universe as a diffuse background field. Still others point to sterile neutrinos, ghostly relatives of the neutrinos we already know, tiny, elusive, and barely there. And then, perhaps, there is something we haven't yet imagined at all. A new layer of physics waiting in the dark. Whatever dark matter turns out to be, it's not a small correction or a rounding error. It's the dominant form of matter in the universe, accounting for about 85% of all the mass. Without it, the cosmos would look nothing like it does now. Galaxies might never have formed. Stars might never have gathered. The great cosmic web, the vast interconnected structure of clusters and filaments, would never have emerged. Dark matter is the quiet architect of existence. It seeded galaxies, shaped the heavens, and gave gravity something to work with. We owe our very existence to its invisible touch. And still, we've never caught it directly. Across the world, deep underground, scientists have built enormous detectors, silent chambers buried beneath mountains and mines, shielded from radiation and noise. They wait in the dark, hoping for the faintest signal, the tiny tap of a dark matter particle colliding with an atom. So far, they've heard nothing, but the silence itself is not discouraging. Every non-detection refines the search, narrows the mystery, points us closer to the truth. There's something profoundly poetic in that silence. The idea that the majority of the universe's mass lies beyond sight, that the most important things in existence might also be the quietest. It reminds us that visibility is not the same as importance, that some of the greatest influences move unseen. Dark matter isn't the only mystery hiding in plain sight. It shares the stage with something even more elusive: dark energy, a force that seems to be accelerating the expansion of the universe. Together, these two unknowns, dark matter and dark energy, make up roughly 95% of everything that exists. Everything we can see: stars, planets, people, oceans, atoms, is only the remaining 5%. That realization is both humbling and exhilarating. It means that most of reality still lies beyond our comprehension. It means the universe still keeps secrets. It means we are surrounded, always, by wonder we have not yet named. Dark matter teaches us to look again, to notice the invisible, to measure the unmeasurable, to trust the quiet pool beneath what we see. It asks us to believe that the unseen is not the unreal, that the universe's deepest truths might be written not in light, but in gravity, in the way space curves and holds, the way galaxies stay tethered when they should drift away. In the end, dark matter is not about darkness. It's about connection. It's the unseen thread that holds the cosmic tapestry together, the weight behind the light, the silence beneath the stars. And maybe that's the real lesson, that the universe doesn't reveal itself all at once. It speaks slowly, softly, through hints and patterns, through the pull of things we cannot see. And if we listen carefully enough, even the dark can begin to glow. Take a slow breath and imagine shrinking yourself, not just to the size of a dust mote or a single atom, but smaller still. Slip past the electrons and protons, deeper than their orbits and charges, into a realm where even the idea of solidity dissolves. Here, the rules of daily life begin to fade, and space itself shimmers with uncertainty. Welcome to the quantum world, a place where particles are not tiny marbles, but ripples in invisible fields, and where mass, that old familiar weight, is not simply something a particle has, but something it earns through its quiet relationship with the universe. Begin by letting go of the idea of space as empty. In quantum physics, emptiness doesn't exist. Space is not a blank backdrop, but a restless ocean flat, on average, perhaps, but alive with ripples and murmurs beneath the surface. Every type of particle is tied to its own field, and those fields stretch everywhere, through every corner of existence. They are not decorations of reality, they are reality. Imagine a still pond. Now, toss a pebble in. The ripples that spread outward, that's a particle. An electron is a small, steady ripple in the electron field. A photon, a gentle wave in the electromagnetic field. A quark, a quick vibration in the quark field. Every particle is an echo of its field's motion, a local disturbance in a fabric that extends across the universe. But what gives these ripples their weight? In classical physics, mass was just a number you looked up in a table, something you plugged into Newton's laws to see how fast a thing would fall. In the quantum picture, mass is no longer a given. It's an emergent property, something that arises from how fields behave, how they interact, and how they couple with other fields, especially the Higgs field, the gentle molasses that slows particles and gives them heft. Mass is not a label. It's a conversation, a whisper between fields. And in that whisper, something remarkable happens, even when nothing seems to be there. The vacuum itself is alive. The empty quantum vacuum is not empty at all. It's a bubbling, jittering sea of potential. Fields cannot stay perfectly still because uncertainty forbids it. Even at their lowest possible energy, they tremble. This is the Heisenberg uncertainty principle in action, the universe's quiet refusal to hold perfectly still. These trembles give birth to what physicists call virtual particles. They blink in and out of existence too fast to be seen directly, but their influence is measurable. They tug on real particles, altering how they move and how they interact. A proton sitting quietly in space is not truly alone. It is surrounded by a cloud of flickering presences, pairs of particles appearing, interacting, and vanishing again, like thoughts passing through a resting mind. You might picture it like this. Imagine walking through a room where invisible people are constantly whispering. You can't see them, but you feel their presence. They tug at your sleeve, nudge your steps, shift the air around you. Those whispers don't weigh anything by themselves, but they change the way you move. The same happens at the quantum level. Virtual particles create a faint drag, a subtle resistance that alters a particle's effective mass. Or imagine a small boat gliding on a lake. The lake is the quantum field, the boat a particle. Even when the surface looks calm, hidden ripples move beneath it. Fish dart, currents twist, and the water itself hums with motion. As the boat moves, it feels those unseen motions. Its path is never perfectly smooth. Its speed and resistance depend not just on its shape, but on the restless medium below. That invisible influence, the push and pull of a field's motion, is the quantum origin of mass. Quantum chromodynamics, or QCD, gives this story even more depth. It's the theory that describes the strong nuclear force, the glue that binds quarks together inside protons and neutrons. Strangely enough, the quarks themselves are very light. Most of a proton's mass doesn't come from the quarks at all. It comes from the fierce energy of the strong force that ties them together. The glue itself gives rise to most of the weight. Think of it like building a house out of feathers, then bolting those feathers together with so many nails and beams that the structure becomes heavy from its own supports. The energy that holds the quarks in place becomes the very mass of the proton. In the quantum world, stability has a price, and that price is weight. This, more than almost anything, captures the strange logic of the quantum realm. Nothing is solid, nothing is fixed. What we call a particle is both a ripple and a wave, a location and a probability. The heavier a particle is, the more sharply focused its wave becomes. The lighter it is, the more diffuse, spread thin across space like mist. Mass determines how tightly the universe allows reality to focus on a single point. Even the vacuum, the quietest possible state of all, has energy. In its lowest condition, the fields of the universe still hum with what's called zero-point energy, the faint baseline vibration that never disappears. This energy might seem harmless, but on a cosmic scale, it changes everything. It may even play a role in the expansion of the universe itself. Imagine your home resting on a foundation that, instead of stone, is made of a trampoline softly pulsing beneath your feet, rising and falling with an invisible rhythm. That's our universe. Space isn't static, it quivers. And those tiny quivers may be what drive galaxies apart, slowly, steadily, endlessly. This idea might sound abstract, but its fingerprints are real. The fluctuations of these quantum fields explain why particles have the masses they do, why the electron is so light, why the top quark is so astonishingly heavy, and why the Higgs boson itself sits delicately at the value it does. It's a fragile balancing act, a cosmic equation tuned to the edge of stability. And yet, even with all our understanding, there are questions we still can't answer. Why these masses and not others? Why is the electron 2,000 times lighter than the proton? Why is the top quark heavier than a whole gold atom? These numbers seem arbitrary, as though written by a hidden hand we have not yet seen. Some physicists suspect that deeper symmetries are at play, perhaps new dimensions, unseen particles, or even parallel universes where the constants of physics take on slightly different values. Still, for all the mystery, quantum field theory remains our most successful description of reality. It tells us that space is not a void, but a loom. Every field is a thread, every particle a knot of vibration, and mass itself is a pattern that forms when the threads pull tight. Which brings us to one of the strangest truths of all. Even nothing has weight. We think of empty space as cold and lifeless, the quiet between stars. But when we look closer, it reveals itself as a restless fabric filled with zero-point energy. The fields never vanish. They hum softly at their lowest tones, even when everything else has fallen silent. This means the vacuum is not truly empty. It contains energy, and therefore, by Einstein's great equation, it contains mass. It's not mass you can weigh on a scale. It's a mass of influence, a weight that bends space and shapes the fate of the cosmos. This leads us to the cosmological constant, a small but powerful term Einstein added to his equations over a century ago. At the time, he believed the universe was static, neither expanding nor contracting. But gravity, unchecked, would have pulled everything inward, collapsing the universe into itself. So Einstein introduced a counterforce, a soft outward pressure woven into the fabric of space, a cosmic balancing act. Later, when the expansion of the universe was discovered, Einstein called it his greatest blunder. He thought he had made a mistake. But decades later, the constant returned this time as the key to explaining something even stranger: the acceleration of the universe's expansion. Galaxies are not just drifting apart, they are speeding away faster and faster. It's as if space itself is exhaling. That push, invisible and immense, is now known as dark energy. And one of the simplest explanations for it is the energy of the vacuum itself. The same zero-point energy that hums quietly in every corner of space. The cosmological constant, once a mathematical patch, may now be the heartbeat of the universe. Think of it like this: the more space there is, the more vacuum energy exists within it. And the more vacuum energy there is, the more expansion it causes. It's a self-sustaining loop, a cosmic rising dough, inflating not with air but with possibility. The more it expands, the more it wants to expand. The process is not explosive, but serene, like a sigh drawn out over billions of years. The idea that energy can exist without matter, that emptiness itself can create pressure and curvature, is one of the most counterintuitive discoveries in all of physics. But the math is clear, and the observations agree. Energy curves space. Curved space guides motion. And what we experience as mass and gravity are born from this quiet exchange. So when you imagine the vacuum, don't picture stillness. Picture a sea of motion, invisible but eternal. Picture every point of space vibrating with the faintest hum, every particle a ripple, every ripple a note in the symphony of being. Mass, in this view, is not a burden, not a lump of substance, but the rhythm that emerges when energy lingers in one place long enough to be noticed. Even the most solid stone, even the stillest night, carries that hum. The weight of a mountain is written in invisible music, the harmony between energy and field, between emptiness and form, And somewhere in that quiet equilibrium, the universe keeps time, pulsing softly to a rhythm older than stars. When cosmologists say the universe is flat, they don't mean it's shaped like a pancake stretched across the void. They mean that, on the grandest scales, space behaves according to Euclid's quiet, old rules. Triangles add up to 180 degrees. Parallel lines never meet. If you could travel for billions of light years in a straight line, you'd never curve back to where you started. That flatness is astonishing. It suggests that the universe, despite all its swelling and spinning, is delicately balanced, neither folding in on itself, nor ballooning wildly apart. Something holds that balance, and many physicists believe vacuum energy, the subtle pressure of empty space itself, plays a role in keeping the cosmic sheet smooth and steady, counteracting gravity's inward pull with just enough outward push to keep the curvature nearly zero. Yet, as elegant as that picture sounds, it hides one of the most jarring mismatches in all of science. When we use quantum field theory to calculate how much vacuum energy space should contain, the answer comes out absurdly huge. So large that it exceeds what our telescopes measure by a factor of 10 to the power of 120. No other prediction in physics misses the mark by so much. This single number, this silent chasm between theory and reality, has been called the worst calculation in science. It implies that somewhere deep in our mathematics, or deep in the universe itself, there is a kind of cancellation we don't yet understand. Perhaps opposing contributions from different fields are erasing most of the expected vacuum energy. Perhaps our equations, brilliant though they are, have missed some fundamental ingredient. Whatever the reason, the fact remains that the cosmos is astonishingly calm compared to what our math demands. Even so, we can see the fingerprints of this invisible energy everywhere. We see galaxies drifting apart, their speed increasing with time, as though the universe were quietly exhaling. We detect, in subtle ways, the faint pressure of the vacuum, shaping cosmic history without needing atoms or light. Empty space is no longer a neutral stage, it participates in the play. It curves without mass, exerts influence without substance, and turns nothingness into something real. The idea that emptiness itself can weigh on the universe stretches every instinct, yet it fits the evidence. It reminds us that energy and mass are two sides of the same coin, and that even silence can have consequence. Following the thread of mass has led us from apples falling in orchards to quarks bound within protons, from the drag of the Higgs field to the jitter of quantum vacuum. And now we find it even in the spaces between galaxies, the vast dark plains we once called voids. They are not truly empty. They hum softly with potential, heavy with unseen energy, expanding gently as time itself stretches them apart. The night sky, with all its stars, is only a lacework draped across this deeper field. The spaces between those stars are not absence but fullness of a different kind. Empty space, it turns out, is the universe's most patient mystery, carrying more weight than anything we can touch. And time so ordinary, so dependable, turns out to share in that strangeness. We like to think of it as universal, a rhythm that beats the same for everyone, everywhere. A second is a second, whether you're reading quietly in bed or circling the Earth in orbit. But that, too, is an illusion born of comfort. Time is elastic. It bends, stretches, and slows, depending on where you are and how fast you move. And mass, The same quiet property we've been chasing through all these scales is one of the main reasons why. It isn't that massive objects carry little clocks that tick more slowly. It's that their very presence changes the shape of space and time. Space and time are not separate things. They form a single continuous fabric, space-time, and mass presses upon that fabric like a weight on a soft sheet. The more massive something is, the deeper the dip it creates. Place a bowling ball on a mattress, and the mattress sags. Roll a marble past it, and the marble curves toward the depression. That's how gravity works, not as an invisible force pulling at a distance, but as a response to curvature. Where space bends, motion follows the bend, and where space bends, time bends too. Near massive objects, the flow of moments slows down. Clocks tick more sluggishly the closer they are to strong gravity. This effect, called gravitational time dilation, was first predicted by Einstein's general relativity and has been confirmed again and again. We use it every day without noticing. Every GPS signal that guides a car or phone depends on satellites high above Earth, each carrying atomic clocks more precise than any pendulum or quartz. But those clocks, floating in weaker gravity, tick slightly faster than identical ones on the ground. Meanwhile, because the satellites are moving quickly, special relativity makes their clocks tick slower. The two effects nearly cancel, but not completely. In the end, the clocks in orbit gain about 40 microseconds each day. That may sound trivial, but if uncorrected, the result would be catastrophic for navigation. Within a single day, your GPS would drift by 10 kilometers, mapping you into another town. To make it work, engineers quietly correct for Einstein's warping of time, a small but constant reminder that physics shapes even our commutes. The slowing of time near mass isn't just a technical quirk, it's a glimpse into the structure of reality. Time is not absolute. It depends on gravity, and gravity depends on mass. Two identical clocks, one placed on a mountaintop, another by the sea, will not agree. The clock at the summit, farther from Earth's center and thus in a weaker gravitational field, ticks ever so slightly faster. The difference is minuscule fractions of a trillionth of a second, but measurable. And when we scale this up to denser worlds, the contrast becomes startling. Near a neutron star, time slows dramatically. Near the edge of a black hole, it nearly stops. If you could hover safely just outside a black hole's event horizon, an hour for you might equal centuries for someone far away. This is not science fiction. Astronauts on the International Space Station experience a minute version of it every day. Time itself, the quiet current we drift through, is shaped by mass. Heavy things not only anchor us in space, they anchor us in time. The very flow of moments depends on the gravity around us. Even simultaneity, the idea that two events can happen at the same time, breaks down in curved space-time. What is now for you might not be now for someone else if their clock is ticking under a different weight of gravity. Why does mass have this power? Because mass is energy, and energy tells space-time how to curve. That simple statement, the heart of general relativity, ties everything together. Mass and energy sculpt the geometry of the universe. Geometry, in turn, guides the motion of everything within it. Space-time is not a passive backdrop. It's an active, responsive medium. And if it were ever truly flat, no mass, no energy, no curvature, time would flow evenly everywhere. But our universe is thick with structure. Galaxies, stars, planets, clouds of gas, and even dark matter. All tug at the fabric in their own subtle ways, changing how time moves through them. Time flows slightly differently at sea level than it does on a plane. It flows differently near the sun than between galaxies. It flows differently for you and for the clock in your phone. There's something strangely comforting in this. Every object, no matter how small, leaves its trace on the universe's rhythm. The ground beneath your feet, the mountain on the horizon, the planet you stand on, all of them slow the beat of time in their presence. Even your own body adds a faint, immeasurable wrinkle to the fabric. You are part of the universe's timing mechanism. Every second you experience is shaped by the mass around you and by the small mass that you contribute in return. And yet, the deeper we explore this connection between mass and time, the more it reveals how much we still don't know. We can measure mass with exquisite precision. We can map how it curves space, slows clocks, and bends light. We can trace its origins to interactions with the Higgs field and to the energy-binding quarks inside protons. We can use it to predict orbits, to calculate tides, to balance spacecraft on interplanetary journeys. But for all that, we don't truly understand what mass is. It sits at the center of physics like a word we use fluently, without fully grasping its meaning. This uncertainty mirrors a deeper rift in physics itself, the uneasy peace between the two great theories that describe our world. Quantum mechanics governs the small, where uncertainty and probability rule. General relativity governs the large, where gravity curves space-time into planets and stars. Both are masterpieces, and both work flawlessly in their realms. But at the edges inside black holes, at the dawn of the universe, they collide. The mathematics refuses to merge. Gravity resists quantization, and quantum fields resist curvature. Somewhere in that clash lies a missing theory, a bridge we haven't yet built. Many physicists believe that bridge might be quantum gravity. Some search for it through string theory, an idea that replaces particles with tiny vibrating strings, each vibration a note that corresponds to a particle's identity. In that picture, mass is the pitch of the string, determined by how tightly it's wound, how fast it vibrates. It's a beautiful metaphor, uniting geometry, vibration, and substance. Others pursue loop quantum gravity, an approach that tries to quantize space itself, turning space-time into a web of tiny loops woven together. Mass, in that vision, becomes a property of this woven geometry. But both ideas remain beyond direct experiment. Their equations more like constellations of thought than testable predictions. Even within our most successful theory, the standard model mysteries remain. We know the masses of particles only because we've measured them. The equations allow those numbers but don't explain them. Why should the electron be 2,000 times lighter than the proton? Why should the top quark outweigh entire atoms of gold? Why such disparity in a universe that otherwise loves symmetry? And beyond that, what of dark matter, the hidden mass that sculpts galaxies? We know it gravitates, but we don't know what it's made of, or why it refuses to shine. It could be a new particle, a subtle echo of the Higgs field, or something stranger still, a hint of a deeper layer of reality. Even the concept of inertia, so familiar from childhood, hides questions. We know that inertia resists acceleration, that it gives mass its stubbornness, but we don't know why. Some physicists have wondered whether inertia might come not from within matter, but from its interaction with the rest of the universe, a kind of dialogue between each particle and the vast cosmic field it sits in. If so, every push and every resistance would be a whisper exchanged across the entire expanse of space-time. In the end, Mass sits at the intersection of physics and philosophy. Is it something fundamental, an intrinsic, unchanging property of matter? Or is it emergent, appearing only when particles interact with the fields that cradle them? We talk about effective properties in physics, things that arise only from large collections or complex interactions. Temperature, for instance, is not something a single atom possesses. It emerges from the collective motion of many. Perhaps mass, too, is like that, a grand average, a behavior that only reveals itself when energy, space, and time agree to dance in the same rhythm. What began as a simple word, weight, heaviness, the pull of gravity, has unfolded into a map of almost everything we know and everything we don't. From the curve of a clock's tick to the stretch of the universe's edge, from quantum fields to black holes, mass ties the story together. It bends, it slows, it hums through the silence between galaxies. It connects the tangible to the invisible, the personal to the cosmic. And though we still chase its final meaning, perhaps that's what makes it beautiful, that the universe leaves us something to wonder about, even as it lets us hold its weight in our hands. Maybe mass is a little like a rainbow. You can point to it, describe it, even measure its shape, but you can't hold it in your hands. It's not an object. It's a phenomenon, born from conditions, the meeting of light and air and water, or in this case, of particles and fields and motion. Mass might not be a thing at all, but a consequence, the echo of relationships too small and fast to see, a whisper between the visible and the invisible, an agreement between matter and energy, a pattern rather than a possession. We speak as if objects have mass, as though it were something hidden inside them, packed into their centers. But perhaps it's more honest to say that objects experience mass the way they experience temperature, or color, or time. Mass is not what something owns, it's how something belongs. Every particle, every atom, every planet participates in this belonging. Mass is not carried, it is performed. It's how matter takes part in the rhythm of the universe, how it folds itself into the geometry of space and the music of time. And because mass bends space-time, because it changes the very flow of hours and minutes, it also becomes something more than a measure of heaviness. It becomes a measure of connection, a way of knowing how deeply something rests in the cosmos. When you look at a mountain, what you see is not just stone, but time moving more slowly. When you hold a rock in your palm, you are holding a place where space bends ever so slightly inward, and the seconds tick a little more patiently. If mass can slow time, then it's not merely a physical quantity, it's a signature, a note in the song of being. It tells us how matter moves, how it ages, how it dances with the invisible fields around it. Maybe one day, when physics finally ties its loose threads together, when quantum gravity and relativity shake hands, we'll see the full pattern, the way mass emerges naturally from a deeper harmony. Maybe dark matter, silent and unseen, will reveal its true shape and show us where the missing notes have been hiding. Or maybe the mystery will remain, a blur at the edges of comprehension, a reminder that even the most familiar ideas have depths we may never finish exploring. Physics has a way of humbling us like that. Each time we think we've reached the foundation, the floor gives way to another level of meaning. The best discoveries often come not from demanding answers, but from changing the question. Maybe we're not meant to weigh reality, but to listen for its rhythm. In that rhythm, mass feels less like a fact to be solved and more like a tone that underlies everything else. It's the baseline of the cosmos, steady, grounding, quietly felt in all that moves above it. Perhaps the goal isn't to reduce it to equations, but to understand it the way you understand a song, not by dissecting the notes, but by feeling the pattern they make together. Mass is a reminder that the simplest things are never truly simple. The chair beneath you, the air in your lungs, the earth that pulls you gently toward its heart, all are woven into a story stranger and more graceful than we first believed. What began as a number on a scale turns out to be a language the universe speaks to itself. It is the conversation between particles and fields, the small negotiations that allow things to exist in harmony rather than drift apart. Even emptiness is part of that conversation. The void hums with energy. Quantum fields ripple quietly in the dark. Space is never still. Within that stillness, mass emerges, not from substance, but from interaction, a weight not of matter, but of presence. Even light, which has no rest mass at all, still feels the pull it bends around stars, arcs through galaxies, tracing the invisible outlines of gravity's hand. Its path tells us where mass hides, sketching the unseen curves of space-time. And through it all, time itself bends. Mountains, planets, black holes, they each slow the universe's heartbeat in their own way. Mass gives time texture. It makes the cosmos breathe more slowly, where the world grows heavy. And in that slowing, there is grace. Mass is not a thing, it's a relationship. A thread stretched taut between what is and what could be. It's a particle's conversation with a field, a star's dialogue with the curvature of space, a quiet pull that keeps everything coherent and kind. Perhaps we'll never understand it completely, not because it's beyond knowing, but because it keeps leading us further in towards subtler and subtler truths. At the smallest scales, particles blur into waves. At the largest, galaxies drift through time that is curved and uneven. Between those two extremes, mass holds the story together. It gives structure to atoms, fire to stars, shape to galaxies, and gravity to our own steps. Without it, there would be no ground, no orbit, no moment to stand within. Mass is the architecture of being, the invisible framework that allows the universe to hold itself. So let's drift for a while in that thought. Imagine the sky not as emptiness, but as an ocean of invisible weight. Each star balanced in its quiet tension, each galaxy held in its halo of dark matter, each beam of light threading its path through curved space. Imagine sailing past the edge of space-time, where clocks slow almost to a stop, and gravity becomes silence. The whole universe swaying gently, stitched together by mass, and you are part of it. Every atom in your body obeys the same equations. The mass in your bones, the spark in your neurons, the rhythm of your heartbeat, they are all echoes of the same universal conversation. You are shaped by the same fields that shape galaxies. Even at rest, you are alive with motion, heavy with interaction, bound to the world by the quiet legacy of energy. So we return softly to the first question. What is mass? Is it a number, a property, a thing? Or is it a whisper, a rhythm, a signature of belonging? Maybe it's all of these. Maybe it's none. What matters is that it holds the world together, that it gives time its pace, gravity its pull, and life its place to stand. Mass, like wonder, deepens the more you look. It doesn't ask to be solved. It asks to be felt. So if this story has kept you awake, let it be with curiosity. And if it has carried you towards sleep, let it leave you with peace. Feel the gentle weight that keeps you anchored, the soft gravity that hums beneath every breath. Everything around you, the dust, the stars, your own stillness is bound in that same embrace. The universe holds you with the same invisible force that holds itself. Thank you for drifting here for a while. And wherever you are, whatever time it is, may you rest easily in that thought. You are cradled by Mass and held always by the stars.